to the course website. So yeah, I'll just take questions starting whenever you guys want to start asking.
Yes, I have question. So I'm having hard time finding the canonical link for the binomial, the homework one. I don't know. So yeah.
So maybe you can walk through with me what you have so far.
So you want me to give you the T, all these things?
Why don't you give me the form that you have for exponential family form for your distribution? And I'll
okay.
down as we go. Yeah, so I'll share my iPad so I can just write it down and confirm that.
Race theory, it's a law.
Okay, I should be connecting in just a second here. Can you see? You can't see my iPad, can you? Hold on, let's try that again. Oh, you can see it. Okay. All right. So yeah, Lola, why don't you get started by reading off to me what you have so far?
So I have exponential.
And so for people who just joined, we're talking about number 2 from homework 1 and the canonical link for the binomial distribution. So you have
Exponential
f of y equals e to the.
So I have y.
Okay.
Log of pi over 1 minus pi.
Okay.
Plus n log of 1 minus pi plus log of n choose y.
Okay. So what's your t of y then?
Is y.
Okay. So your t of y is equal to y. And what about your theta?
Log of pi over 1 minus pi.
Okay. And your b of theta?
Negative n log of 1 minus pi.
So this all looks pretty good to me. So you're asking about the canonical link. So I think maybe, correct me if I'm wrong, but maybe you're sort of confused about what the canonical link means.
Yeah, I'm still confused about that too and how to find it.
So it's really just a definition. So I was talking a little bit about this in lab about the difference between the natural exponential family form and the exponential family form. The natural form, I'll just call NEF here. You'll have an exponential of something that looks like y of theta minus b of theta over a of phi plus some c term. And then for the more general term, the not what we wouldn't call the natural exponential family, just general exponential family, the form's going to be pretty much exactly the same, except now that's where you have t of y times theta minus b of theta over a of c. So all that I mean when I say the canonical link is if you have a natural exponential family form, then, so this form up here, sorry. If you have this form, the canonical link will be the function of your original, whatever function of your original parameter that theta is equal to. So say you're using mu is the parameter in your original distribution and you get theta equals mu squared right up here in this natural exponential family form, then your canonical link function is the square of your original parameter. If you were to instead have, say you're working with lambda as your original parameter and you get theta equals 1 over lambda, then 1 over lambda is your canonical link function. Does that make sense? And so when you're working with the Poisson distribution, for example, you end up with theta equals log lambda. And so the log function is your canonical link function in that case. Does that make sense?
Yeah, it does.
And so it's more of just a definition of these different parameters when you put it in this form. So does it look to you like the binomial distribution here is natural exponential family or the general exponential family?
The natural.
Yeah, because you have this t of y equals y. So that means you can get the canonical link from this, from putting it into this form. And that's going to be given by your term here. So you may have seen me putting like, say like g of lambda and then equals lambda squared. What I'm saying, so all that I'm doing when I'm doing that is, so g is sort of the generic notation that we use for link functions in GLMs. So g of x, or maybe x is not the right variable to use because x is usually your covariates, but g of z, where z is just some variable, g of z is just the link function applied to some variable z, and that can be any function of that parameter z. So if you have a log link, then that would just be log of z. So does that make sense?
Yeah. So does that mean that in this case it will be the, for example, g of I don't know, the parameter is, so g of pi will be log of pi over 1 minus pi, something like that.
And this function, yeah, so this function g of pi equals pi over 1 minus pi. Sorry, I forgot the log there. That's called the logit function when you have a log of something over 1 minus that thing. And that's actually where the name logistic regression comes from, because the logit function is the canonical link for binomial data.
That makes sense. Thank you.
Welcome.
And so just to follow up on a question here, so the log is technically the link. Is that correct out of this? Or is it both like the log pi over 1 minus pi?
So the link is the entire function on the right-hand side of that equation.
Okay. Okay. Thank you.
Could we go over the expectation and the variance for this? Because one of the things that I did next was then express pi as a function of theta. So I could continue to try to get the expectation and the variance. But then I got kind of lost after that.
Yeah, that's totally fair.
Because when you are actually getting your expectation and your variance, it's as a function of your parameter of interest, right?
Yeah, and so you can actually do it either way. And because of the invariance of MLE's property, it will work out to be the same. So you take the derivative first and then replace your pi with that function of pi that's with your theta, or you can replace it and then take the derivative. And in a lot of cases, it turns out to be easier to take to replace it with theta and take the derivative then. But in some cases, it's easier to do it the other way around.
Okay.
And in this case, it's actually easier to take the derivative first and then replace with the theta.
Okay.
So, and I mean, we can walk through it. I would say that in this case, it's just about being like super careful and like kind of checking your work at each step, because it's easy to make mistakes because there's a lot of like algebraic transformations.
Yeah, I think I did it the other way. So like I wrote pi as a function of theta first and then did the derivative. And I think it's probably easier, like you said, the other way around. Just take the derivative of negative n log of 1 minus pi, right?
And for logistic regression, the pi actually ends up being your probability. And we'll talk about this in the next couple of weeks, but you can get both odds ratios out of logistic regression, which are your beta coefficients exponentiated. And you also can get your probabilities, of observing your outcome. And this function here is how you get between the probabilities and the log ratios, the odds ratios. So you actually do end up working with it a little bit. So it doesn't have to be like sort of comfortable, like transforming between this theta equals log pi over 1 minus pi, and then finding that in terms of theta. But I would say try to get the expectation and variance by taking the derivative first in this form and then replacing your pi's with thetas, and try doing it both ways and see if you get the same answer. It's good practice.
Okay.
I'm going to erase some of this so I have a little more space. Unless you guys are copying it down, and then I'll just start a new page. Okay, any more questions?
Could you go over, I don't know how much you can give away about this, but for number 5, I'm just having a hard time getting b of theta to be subtracted from ty theta.
Number 5, the negative binomial.
Yeah.
So can you do the same thing and sort of walk me through what you have right now?
So I got to
okay, so you have
I have it exponentiated and I got it to y log of 1 minus beta.
So is this in the exponential?
Yes.
So you have y log 1 minus y beta. Okay.
And then plus m log of beta.
and then plus log of the y plus m minus 1, and then m minus 1. And I wasn't sure if this is one of those situations where you put, like, you pull like a negative value out to make a of phi -1 to try to, but is that kind of the direction that you had? But then that makes,
Well, let's
it
try
so
it both ways.
okay.
This is one of those situations where you sort of just try it out and see what works. So what's our t of y?
I had it as equal to y.
And then theta.
Theta would be log of 1 minus beta.
So then beta in terms of theta is going to be e of theta so that seems okay to me. We can transform from theta to beta, and we don't end up with something like taking a log of a negative number or anything like that.
Okay, then I must have just made some mistake in there.
So then b of theta term. Oops. Is going to be what?
It would
Negative.
be of theta. It would be negative log of 1 minus e to the theta.
Yeah, so that looks pretty good to me. The only red flags I would worry about are if you're doing something with this function here that is sort of mathematically not valid, like taking a log of a negative number. And I don't see any red flags here.
Okay, thank you. I think I was overthinking it.
Yeah, no problem.
On this particular problem, so then we would say that the canonical link is g of beta equals log of 1 minus beta.
Mhm.
Okay. I feel like I've been overcomplicating it.
That's why office hours can be helpful.
Okay. All right. Sounds good. I think I'm getting it.
Awesome.
Can I ask a question about just homework 1 overall? I don't know if I dreamt this or not, but on the first day of class, did you say it was acceptable for homework 1 to scan in our handwritten work, or do you want this all typed up with LaTeX or something?
Yeah, it's acceptable to scan in your handwritten work. That's fine with me.
Wonderful. Thank you.
I'll put that in an announcement too for anybody who's confused about it, but it's certainly easier for the TAs to read it if it's typed up, but I get that there's a lot of derivation with this homework in the next, and that might not be a good use of your time, so it's fine if you scan it. Just try to write it neatly. Yeah, so I'll add that to the announcements too. I just need to make a note for myself.
So back to the canonical link, when you went over the normal distribution, the theta is just equal to mu, which is understandable. So in situations where your theta and your parameter of interest are equivalent to each other, do we just say like g of mu equals theta, like as simple as that? Or
Yeah, and so actually you would say like g of, in this case, g of beta equals log 1 minus beta,
Mhm.
or g of mu equals mu.
Okay.
So in the case you're talking about, which is called the identity link, then what I have boxed here would be sufficient.
Okay.
Any other questions? I'm happy to take questions about homework 2 today, if anybody's here for that.
Julia, did you already work through number 3 with the Poisson distribution? Everyone?
I have not worked through that one.
Okay. I think I'm just mixed up with the theta on this. I can share what I have as well for this
Yeah,
problem.
sure. That sounds great. Let's start there.
Okay.
So I think I'm finally getting the hang of the iPad. This is exciting. So, okay, what do you have so far?
So I have the exponent of y log of lambda minus lambda minus the log and then y. Yeah.
Cool.
And so I have t of y equals y. And then my theta was log of lambda. Okay. Okay. Now I understand that.
What was the confusion?
The log of lambda and then having to your lambda equals e of theta.
You mean from the homework or?
Yeah. Yeah.
From homework 2?
Oh, no. This is still on the same problem, but I just realized what I did wrong with this.
Oh, okay, great. The first homework problem, actually the entire homework 2 does a lot with the Poisson distribution.
Okay.
And so this is another one of those distributions where it's in the natural exponential family, and the canonical link, which is here, is the link that's used in Poisson regression.
Okay. That makes sense. Perfect. Thank you.
No problem.
Is based on this information, is the b of theta equal to lambda? Because I mean, based on the way that the exponential family form is currently right now, like it's what it seems to be, because it's minus lambda, right? So it's just lambda.
That's right.
Okay. And so then the link function here would be g of lambda equals log of lambda.
That's correct.
Okay.
Oh, this is interesting though. So you actually are going to have to put b of theta into the form where you have
Yeah.
theta as the parameter to get the expectation and variance.
Right. Otherwise, your
Yeah.
derivative of b of theta would be 1, which doesn't make sense.
Exactly. So you're going to have to ignore what I said about the binomial distribution and use the version with theta in it.
So I think some resources that I was looking at, like the textbook, like one of the books might have it that you always change it, like you always change theta as a function of whatever parameter of interest you have. And then there's the derivative. That's why I was kind of confused as to like which one to do first.
Can you tell me which textbook you're pointing to and which page?
No, I honestly can't even remember. I just eventually started, like, every time I have a theta and I pull it out from the exponential function, like I immediately transform that to it being a function of theta. So like here, the first thing I did, as soon as I got my theta equals log of lambda, the first thing I did was did lambda equals e of theta. Like I always do that before and then I plug it in like that in the b of theta, and I also plug it in like that in the derivative and then the second derivative. So that's kind of how I've been doing it, which
That's right. Yeah, that's the correct thing. That's the right thing to do.
okay. But yeah, because I've seen it done the other way around too. I don't know where, maybe in class or somewhere. Yeah. But you would recommend doing that first and then just kind of following it like that.
Mm-hmm.
Okay.
I have a quick question about homework 2.
Sure.
And I haven't actually done it yet. I was just looking at it, but I wanted to see if this is like the right way of thinking about it. So like questions 2 and 3, where you're still using a Poisson distribution. Actually, is 3 also that?
So is it Alex who's talking right now?
Yeah.
Okay, great. There's some like a little bit of a disembodied voice going on, and I think there's a lag from
Oh, sorry.
which Zoom window is getting highlighted. So I'm just trying to make sure I know which of you is speaking. Okay, thanks. So you're talking about homework 2 and
Yeah.
2 and 3, you said?
Yeah. Are they both assuming a Poisson distribution?
So sort of. So that's kind of what I was
So but number 3 is as well too. Like you could say
yeah. So number 3
that.
is cool. You assume that the y's follow a Poisson distribution, and
Okay, so my thought was that you want us to use the Poisson distribution given at the top, but when we write out like the joint probability, like that function will change because the y's change, right? The outcome.
do you mean like for number 2 where I'm asking for the likelihood function?
Yeah.
Mm-hmm. Yeah.
Like to derive the likelihood function, we can basically use the same exact distribution as what's given, and then We just have to alter it when we're calculating like the joint density.
So I can give you a hint on this because I'm going to go through a hint in lab anyway.
Yeah, that'd be great.
And so basically, if you take the y's, we know that y follows a Poisson distribution. Which is a discrete probability distribution. With this PDF, or PMF technically, y's can be from, are integers that can be from 0 to infinity. And then, so in number 2, they tell you, okay, we're going to define a new variable. The homework calls it yi star. I'm just going to call it zi. And that's based on an indicator function. And so indicator functions are a way of binarizing continuous variables. So if you have indicator of yi equals 0, what that means is that zi is equal to 1 if yi is greater than 0, and zi is equal to 0 if yi is less than or equal to 0. And since this is a Poisson distribution, which can only take values from 0 to infinity, that means that zi is going to equal 0 when yi is equal to 0. Does that follow so far?
Yep.
And so what distribution do we use for binary data?
The binomial.
So we can use Bernoulli or binomial. Bernoulli typically is when you have like multiple successes or failures sort of summed up, and binomial is when you just have sort of a single coin flip, a single 0 or 1 that you can get. And so zi can take on values of 0 or 1. So now zi is actually a variable with a different distribution. Because it's binary, you can think of it as following a Bernoulli distribution.
Okay.
And so what's the parameter that you're interested in when you have a Bernoulli or binomial distribution?
The probability.
So in that case, you're interested, usually it would be the probability that zi equals 1. And you can call that parameter p or pi.
Okay.
And so the trick here is to figure out how to use what you know about the distributions of yi's to figure out what p is in terms of lambda. And so you can use the
What p is in terms of lambda.
So what the
And then can we use like the binomial approximation?
So you can actually use the Poisson distribution directly. And all the information that I have written down here. So because the Poisson distribution is discrete, what f of y really means, you can write this, is what we have is the probability y equals y is lambda to the y e to the negative lambda. So this wouldn't work if y followed a continuous distribution, because when y follows a continuous distribution, you assume that point masses are at 0, meaning you can't have like sort of sub in a particular y value. But with discrete distributions like Poisson, it's actually a mass function that follows this. So like you often see f of y written down, but for discrete distributions, what that means is the probability y equals y. What it means for, does that make sense?
Yeah.
So if you just keep following me, so we know that y can only take on values of 0 etc. And we also know that when y is greater than 0, zi is equal to 1, and when y is equal to 0, zi is equal to 0. And so from this equation, we can calculate pretty easily the probability that y is equal to 0. By plugging in 0 for y in this right-hand side. And if we have probability of y equals y, well, what is probability of z equals 0? What is the probability of z equals 0 based on this?
Isn't that the same thing?
Mm-hmm.
And then the probability that z equals 1 is 1 minus that. That totally makes sense.
So then that gives you your p parameter that that defines your likelihood function for the Bernoulli distribution.
Okay, that makes sense. Yeah, I couldn't figure out how to relate that to lambda itself. Okay, super helpful. Thank you.
Yeah, no problem.
I have another question about homework too, and for the first problem, when you ask for the information, it's part C, the expected information about lambda. Can you describe like kind of how specific we should be? Like, are you looking for a function of lambda generally, or a function of lambda hat, like the MLE, or even like the numeric value?
I would put it in terms of lambda hat and the numeric value based on the information that you're given above.
Okay. And when we look at the formula for expected information, do you always put in lambda hat, or that's like a step beyond deriving the expected information? So like the expected information will give you a function of lambda, and then if you want to have is this correct? Like if you want to have the information at the MLE of lambda, then you would put lambda hat into the formula?
That's right.
Okay, got it.
Practically speaking, people usually evaluate it at the MLE because that's how you get confidence intervals and stuff like that. But you don't have to put it in that form always.
Okay, and then the variance is just the inverse of the information, the expected information, correct?
Yeah, if you have more than one parameter, it's going to be you're going to have to like invert the matrix. So it'll be a little bit different because you'll have like a variance and covariance matrix. But when you only have one parameter, it's just 1 over the information.
Okay. And that's an approximation, right? It's like
Mm-hmm.
the
asymptotic variance of your estimator. So it'll be better when your sample size is larger.
Okay, cool.
Mm-hmm.
Back to the previous example that you just showed with like number 2 on the homework. Does it matter if you relate lambda to the probability that y equals 0 or y equals 1? Like the probability that z equals 1, like that is the probability
Are you asking if it matters if you put the likelihood in terms of lambda?
I'm asking if it matters if like the probability is like an 80% chance of 1 and 20% chance of 0. If it matters if you use the probability of 0 versus the probability of 1.
Oh, and how you define the
Yeah, because like all of these distributions have like a bunch of different like parameterizations and
mhm. I mean, it's typical, it's more typical in the case of Bernoulli or binomial to define the parameter in terms of the probability that the variable is equal to 1, probability that
Okay.
y equals 1. So I would do it that way. And that's
Okay,
that's how
that
they
makes
have
sense.
it often defined and usually defined in logistic regression too.
Okay. And then like because 3 has like the probability that y equals 0.
Yeah, then it's defined it's just, they happen to find the parameter in that way, but because you'll have calculated that in the previous question, you'll sort of know what to plug in there.
Okay, cool. Thanks.
Mhm.
For homework 1, I had a question.
Sure.
I was a little confused by what phi is in number 3 for the Poisson distribution.
Sure. So we have that written out right here, actually. So
Oh, sweet.
it's already, we don't have phi written out. So what form do you have for your exponential family distribution?
I've got the exponent of y log lambda minus log 1 over y exclamation point.
So, and then what do you have for each? So, what do you have for each of the other, each of the pieces? So like T and Y and theta and everything.
Yeah, so the for theta, I've got log lambda. Ty would just be y, right? And b of theta, I've got lambda for that as well.
Mhm.
But since I didn't have anything as a denominator, I wasn't sure if phi would just be 1.
It's okay to have a of phi equal to 1.
If equal to 1. Okay.
So some distributions don't have like an extra parameter. And so like in the normal distribution that ends up being sigma squared is part of that. And just some distributions just don't have that. They only have the 1. You'll see the same thing with the binomial distribution. You might have like A of G equals to 1 or equals to -1, but not an extra parameter.
So as long as we're kind of able to justify or show it in our work how we got somewhere, does that sort of count towards even if we end up with the wrong answer?
Mm-hmm. Okay. Yeah, you'll definitely get partial credit.
Okay, that's good to know. For the variance on that one, if we're taking the second derivative of b of theta, I was a little confused if I should just leave it like that.
So this is where we were talking, this came up just a little bit earlier.
I
And
apologize. I was wait.
so then lambda in terms of theta is going to be e to the theta. And b of theta in terms of theta is going to be e to the theta. So in order to get the expectation of and variance, you have to take the derivative of this equation. Otherwise, if you take the derivative here, you're going to end up with a variance of 0, which should give you sort of alert you to the fact that something's probably wrong. A good way to check your work is to take a look at what expectation and variance you get, put it back in terms of the original parameter. So here, if we take the first derivative of b of theta, which is equal to derivative with respect to theta of e of theta, you get e of theta again, because that's the derivative of e of theta is just itself. So putting that back in terms of lambda, you get lambda. And if you look at Wikipedia or somewhere else for the expectation of a Poisson variable, it's lambda. So that is a good, like a sanity check to know that what you're getting is what you should be expecting to get. And so you should get the same thing. When you look at the variance, you can sort of check to get your work that way to make sure your answer makes sense.
I see. Thank you.
For the homework assignment, do we have to express expectation and variance in terms of theta or the original parameter of interest?
You can express it in terms of theta.
Okay.
This is just an extra step, sort of to check your work and make sure everything intuitively makes sense, if that is helpful to you.
Okay, thank you.
Any other questions about homework 1 or 2? I'll be here.
I'm trying to work through the derivative of the binomial distribution, so I might need some help here in a minute.
Sure. Yeah, I'm just playing around with the settings here.
I think I'm having a hard time with the manipulation of pi in the binomial distribution.
Mhm.
I can read it off to you. That would help.
Yeah, sure. Let's we can work through it together. So
The theta is equal to the log of pi over 1 minus pi.
so let's just start from the beginning. And can you read off what you had again for your exponential family distribution for me?
Yeah. So I don't know if are you able to write, because I can't see your screen, which is fine.
Oh yeah. I have to remirror it. Sorry. It should connect in just a second here. Okay, can you see it?
Yeah, I can see it now.
Okay, great.
Okay. That would be y log of pi divided by 1 minus pi.
Okay.
Plus n log of 1 minus pi. Plus the log of n choose y, I think is how you say that.
Mhm. Okay. So okay. So what
Yeah,
did you get when you rearranged this?
when I rearranged it, I got e pi over 1. I'm sorry, pi equals e of theta over 1 plus e of theta. So that's good.
Wait,
I think,
I just wrote that wrong.
yeah.
So
So
you got pi equals e2 to the theta, you said, over 1 plus
yeah,
e to the theta.
yep. got
Okay, so then in terms for the b of theta, you get n log 1 minus e to the theta over 1 plus e to the theta.
Right. I believe that that's a negative though. The b of theta because of the way that it's set up on the exponential equation.
Yes, that's correct. So you can probably manipulate this a little bit to make it a little nicer. I would. Does this make sense what I'm doing?
The second part does, but I don't know why the first one does not.
So basically I took this 1 here and I
Mhm.
made that into 1 plus e to the theta over 1 plus e to the theta.
Oh, so you can have a common
Minus.
denominator and actually, okay,
Yeah, exactly.
okay.
And then that allows me to combine, get to this step here. So then I can combine everything. So I don't have, so I have everything under one denominator.
Right.
And because of that, then I can split up the log term. And you get minus n log 1 plus n log 1 plus e to the theta. And so what does that equal?
Wait, I think I'm one step behind you.
Yeah, no,
Trying to still process.
take your time. Just go through and
So we're still not even taking derivatives. Like at this point, we're still simplifying.
we're still simplifying. You haven't taken the derivative yet. Sometimes it's easier to simplify first.
Mhm.
So are you with me and to this step right here?
Yeah, I understand the separation now. Yeah.
So I can simplify this further. Do you see how?
No.
What's the log of 1?
Thought it was 0.
That's right. So that means that this term is going to
Goes
go
away.
away.
Okay.
And then you're only left with this part here. And so that looks a little nicer than this, right?
Yep. Okay.
So I'll switch to another color because why not? So now if we want to calculate our B prime of theta,
The n stays out, right? Like, because it's not part of the log.
yeah, you can treat that as a constant.
Gotcha.
And then you can use the chain rule to solve for this. So why don't you work that out and let me know if you have any questions? Does that sound good?
Yeah, the biggest problem I have with that is just the n. It's like treat it like a constant using the chain rule. Because to me, when I take the derivative, immediately want to turn it into the derivative of a constant is just 0. And I think that's what's messing me up.
That's not always true though. So the
Okay.
derivative of a constant on its own is 0. I like to think about it in terms of, let's say if you have like, you want the derivative with respect to x of 2x,
Mm-hmm.
and then the derivative with respect to x of 2x plus 2,
Mm-hmm.
right?
Gotcha. Yeah.
So derivative of 2x is going to be 2 because you have whatever constant, and then the
Mhm.
derivative times the derivative of x is 1. But with this one here, you carry the derivative to both terms. And then in this piece, you're just taking the derivative of a constant with no x. You can
Okay.
also think about it in terms of plots. So when you are taking the derivative, you are really finding like places where your line sort of flattens out. Well, okay, I'm not gonna ignore that for now. That's gonna be, but does,
I think it does make sense because I mean, what thing we're trying to say is that it's gonna be different whether it's part when it's actually paired with something else as opposed to just taking it by itself, like I was just talking about. That was confusing me.
yeah, I would review the rules of derivatives here.
Yeah, I think
Because that's one that I would even like when you're going through this stuff, just have this sort of sheet next to you. It'll make things go like a little bit easier.
okay. Sounds good. Let me try that derivative.
Quotient rule, that sort of stuff.
Yeah, I'm gonna try that derivative real quick. The n log 1 plus e theta.
Julia, I'm just working through the derivatives for number 5. And I think, is it okay if I just walk this through with you? Because I feel like I'm missing a step here.
Yeah, sure.
Okay. I know that we went over that first part, but I can go over that one more time with you for the manipulation.
That sounds good. And I'm just gonna put this back up here and we can come back to it.
Yeah,
So
that sounds good.
Katie, you're asking me about a negative binomial, and Bezida, you're asking about binomial, right?
Yep.
It's just
Yeah,
takes
that's
time
correct.
for the like Zoom window to switch and tell me who's talking. So I'm sorry for that.
Oh,
But yeah, so Katie, I can walk you through that. And Bezida, if you have any problems with that derivative, just let me know and we can come back to it. I won't erase
Okay.
it.
Okay, thank you.
Yeah, so Katie, where are you at right now?
so I've got, for the most part, I've manipulated this and I think I have my theta. What I'm caught up on right now is just giving my expectation the variance as well with the derivatives. So I can give you that first part again, and we can just go from top to bottom if that makes it easier.
Sure, that works.
Okay, so I have the exponent of y log And then in parentheses, I have 1 minus beta plus m log beta plus log, in parentheses, the numerator would be y plus m minus 1. And then the bottom is m minus 1. Yeah.
Okay.
So then the t of y is y. And then I have the theta of log, in parentheses, 1 minus beta. And so like my basic understanding is that beta is e to the theta.
So not exactly.
Okay.
You need to get beta in terms of theta based on this equation here.
Okay. So then beta would equal.
So we can do step by step. The first step is to take the log of both sides. Or sorry, to exponentiate both sides to get rid of this log term. And so that gives you e to the beta equals 1 minus beta.
Yeah, okay.
And then the next step is to isolate beta.
Okay, so then it would be beta equals 1 minus e to the theta.
Mhm.
And then I need to incorporate the logs, correct? Or do I just leave it in that form?
So based on this equation, yeah, so this is just, you're just transforming between the two variables. One is theta in terms of beta, and the other is beta in terms of theta.
Okay.
There's no like needing to take the log or anything. It's just, this is just putting one variable in terms of the other. So when it,
Okay.
So then you have your b of theta term as well, right? What is that going to be?
So my b of theta term is negative m log of, and then we would plug that in. So it'd be 1 minus e to the theta.
So this is, yeah, exactly. So this is where you want to plug it in.
Okay.
And then for your expectation, you're going to want to take the derivative.
I think this is almost similar to where we're caught up on the other binomial distribution.
Yeah,
it's the m factor. Yeah.
Mhm. So this is where you're stuck right now?
Yeah. That's exactly where I'm stuck at.
So can you walk me through your thought process?
So I think for next steps, I would have to isolate these two factors, right?
What do you mean by two factors?
So the 1 minus e to the theta would technically go to, like this would go to a fraction, right? So I would have like negative m times e to the theta over,
I'm going to walk.
or is that not the right? Okay.
So if we go back up to what I was doing earlier, So I did combine some terms here, going from this step down to this step in this box I'm highlighting. That wasn't necessary. We could have just taken the derivative right here. It's just ugly and it's going to be messy. It's going to be harder. So I'm just simplifying the equation here, which I noticed that I can do in this case. I have, but that's not always going to be something that you can do. So in the form that you have down here, this is already in pretty simplified form, 1 minus e to the theta. There's not much more you can do with that.
Okay.
You could put them all with the same denominator by saying getting e to the theta over e to the theta minus e to the, but that, I mean, they do have a common denominator of 1 right now, actually. But I think that maybe you're getting tripped up by that step, but there's really, so at this point, like, you really can just take the derivative.
Okay, instead of trying to simplify this even further.
Yeah, and so, I mean, what I would do is, I always try to simplify it if I can, just because it makes things easier, but that doesn't mean that you have to. You can, once you have substituted in the parameter theta, you can go ahead and take the derivative.
Okay.
And again, m is a constant here.
Yeah.
So we can pull that out, and then we're just taking the derivative of this log 1 minus e to the theta term. Do you want to walk through that and or start working on that, and I can answer any questions if they come up?
Yeah, that's helpful.
I did something wrong. I don't know what it is, but I think it's wrong. So I'm looking up the chain function, and but like I'm remembering now. It's all coming back to me. I guess I didn't realize it was a chain function. I think that's one of the things that confused me. So my inner function is 1 plus e to the theta, and then my outer function is log of x, basically, right?
Yeah, that's
so
right.
then the first thing I got to do is take the derivative of that log with respect to my inner function, which the log of a value, the log of x is equal to 1 over x.
Yeah, that's right.
So then I would think that, so yeah, you keep the n, and then we do 1 over 1 plus e theta.
Yep.
And then times the derivative of my inner function, which I believe to be e to the theta.
Yep.
But it doesn't seem right. That's what I got.
Oh, that looks great to me.
But I feel like I'm back to the parameter that I was working with to begin with. Like it. Oh no, never mind. That does not look the same. Okay.
There's no more log.
Yep, I'm very rusty, obviously. I see it now. Okay.
You'll get used to it.
Yeah, I'm already getting better at it. And then just take the second derivative of that. So I'll take the second derivative of that, and try to work with that. I don't know
Other
how to
than
work
dealing with the quotient rule, which I never remember.
Okay.
I find it helpful to write the denominator out like this. So 1 plus e to the theta to the -1. And then I can use the chain rule to deal with it that way.
Is it technically chain rule? Yeah.
It's still going to be the chain rule.
But
I guess there's a product as well.
Yeah, because I would think that the chain rule only applied to that -1. Like that's my outer function, right? That exponent.
Mhm.
And then my inner function is that in the parentheses, but then I have the NE theta on the left-hand side. And so that's,
So yeah, you'll use the chain rule on the product rule for that.
okay, sweet. I'll try that for a minute.
I just got kicked off.
I'm not applying the product rule of the left-hand side of it. I'm applying the product rule. I guess I'm not, I started doing the product rule of NE through theta,
Uh-huh.
which I don't think is right. Because then that would be, yeah, no, I think it's literally the product rule using NE of theta as one of my functions. And then the second function would be a composite function, 1 plus E theta to -1.
That's right.
Right.
Yeah.
Okay, yeah. Okay, so I was doing it wrong. All right. One moment. I think I'm gonna get it.
I needed to refresh myself on all this stuff too when I went back to grad school because it had been a couple of years.
It's been way more than a couple of years for me, but we're getting it.
Me too. All right, I'm going to jump off here and keep working through this. Thank you so much for your help, Julia.
Yeah, no problem.
I think I got something. So this is really funny. So the second derivative is, so my first function is n e of theta, and my second function is the composite function 1 plus e theta minus 1.
Yeah.
So the first thing I did was go ahead and take the derivative of each, just so that I had them in hand. So then I could then use that information to apply the product rule.
That's great.
So so derivative, perfect,
And then you have f prime of theta.
is I have e of theta.
Not quite.
No, this is where I messed up. Okay. Yeah, okay. So then now g prime of theta is equal to negative, and then the parentheses 1 plus e of theta to the -2 power
Mm-hmm.
times e of theta.
Yeah.
Okay, so
So
where
I
did I
think
miss?
in this first part, you're just missing this n, like you're dropping that n term. But if you have a constant times your function, you still need to carry that constant over when you're taking the derivative. Just like I was talking about with the derivative of 2 times x is 2. You need to carry over you can't just drop the n. So does that make sense?
Yeah, I think it's confusing because the derivative of x is indeed 1, right?
Mm-hmm.
But the derivative of e of theta is e of theta. So I think that's why it's confusing me, because I'm trying to use that same logic, but it doesn't quite correlate.
So the rule is if you have some constant and times then some function of your variable theta, the derivative with respect to theta of that whole term is
Mhm.
going to be the constant times the derivative of with respect to theta of the function.
Gotcha.
So then when you had, f of 2 times theta, you pull out the 2, and then the derivative with respect to theta of theta is just 1, so you end up with 2. And then when
Okay.
it's 2e to the theta, you end up with 2e to the theta because the derivative of e to theta is e to the theta. Does that help? So I think of it in terms of
Yeah.
like this rule here.
Yeah, I think it makes that's ringing a bell now. Okay. So then now we have the derivative with our functions and the derivative of those functions. Then I take the first function times the derivative of the second function. So f of theta
Yeah, so yeah, you're gonna have f of theta first times the derivative of the second plus the second times the derivative of the first.
That's correct. That's what I have.
Yep. Okay, then you're doing great.
And then I can simplify. I'm gonna simplify as best as I could. Let's see.
Yeah,
And
you
then,
can
but yeah,
simplify it. If you don't simplify it, that's okay.
okay. Yeah, because I mean, technically it's just the second derivative, so we can find the variance. And then my function a of phi is 1, so that should be pretty straightforward. But okay, let me go ahead and write this down real quick. Okay, I wrote it down. Julia, do you think I could ask you some other questions related to the lecture, but would you mind if those were not recorded?
Sure, and I gotta go in a couple minutes.
Okay.
But I can, I'm gonna stop the lecture recording